In the first situation on the document, we say that there's a 3 kilogram mass being acted on by 5 meter per second squared force in its direction of motion. Now, this mass is assumed to be moving on a light beam at a distance of 90 centimeters from the axis, and it's assumed to move 30 centimeters along that arc. But the point is that we have this mass accelerating at this rate in its direction of motion, so that the net force is this product, or 15 newtons. Net force acting on this mass. Now, we don't know what it is that's exerting that force. It could be a direct force acting right on the mass. It could be the result of a torque exerted at some other point on this beam, so that the beam is exerting the 15 Newton force on this mass. Could be that or any combination thereof. So, in any case, the net torque on this object is 9 meters, 0.9 meters times 15 newtons. It's 0.9 meters from the axis of rotation, and the force we just found to be 15 newtons. So that's a 13.5 meter newton torque. Now again, that torque could be produced by a force acting directly on the 3 kilogram mass, or by an equal torque, it turns out, acting anywhere with a force applied at any point along the beam that produces a torque, and then the resulting force would be exerted by the beam on the mass, and the torque acting on the mass would still be this. Now, if the beam is of negligible mass, negligible moment of inertia, then that would be the net force, and that would be the net torque on the entire system, because there would be no mass or no significant mass in the beam to be accelerated, just the mass, the 3 kilogram mass. Okay, so we want to calculate how much work is being done. Okay, well, we can easily calculate the work if we assume that this force acts directly on the mass. Well, the mass is 30 centimeters from the axis. The mass moves 30 centimeters. It's 90 centimeters from the axis. That's not relevant right now, okay? The bottom line is, if the net force acts directly on the mass, then it acts through 30 centimeters. So we have a net force of 15 newtons times 30 centimeters, and that comes out 4.5 joules. Now, we could calculate the same thing based on the radian measure of the motion, the angular motion. Okay, so 30 centimeters, if the beam rotates through 30 centimeters at a point, if the mass rotates through 30 centimeters at a point 90 centimeters from the axis of rotation, then by the definition of a radian, it goes through 1/3 of a radian. Okay, 30 centimeters divided by the 90 centimeters you would have to move at the 90 centimeter distance along the arc to complete a radian. So it's 30 centimeters divided by 90 centimeters per radian gives us 1/3 of a radian. So that the angular displacement is 1/3 of a radian. Now, we calculated previously that F net delta S could equal 15 newtons multiplied by 0.3 meters, that's our 30 centimeters, and that's 4.5 joules. We also could calculate tau net delta theta equals net torque 13.5 meter newtons times 1/3 of a radian, and that also comes out 4.5 joules, because the radian multiplied by a meter and when you're calculating the torque, the meter would be thought of as a meter of radius out to a certain point. So the radian times a meter of radius gives you a meter of arc, so you move along so many meters of arc. Your unit meter newtons becomes then newtons times meters, because again the meter of arc times the radian gives you the meter of radius times the radian gives you a meter of arc. Multiplying that out, you get newtons times actual meters, which gives you 4.5 joules. Okay. Now, we then assume, and this is a different situation with some of the same parameters, we assume that we move through 30 centimeters. Now, we first assume that the net torque is still the same, but we move through 30 centimeters at a distance only 10 centimeters from the axis of rotation. And we see what that would do. Okay, so we get still net torque is your 13.5 newtons from here. But now that's 10 centimeters times the force that's being exerted. So the force would have to be 135 newtons. Just solve this for F2, very easy. And it's pretty easy to see if you're exerting, or if you're producing this torque by a force acting at 90 centimeters from the axis, then if you want to produce the same torque only 10 centimeters from the axis, you're going to need 9 times the force. And this is 9 times the force. Okay, so now if we move 30 centimeters on the arc, okay, if we move 30 centimeters on the arc, then first place, the work done is 135 newtons times 30 centimeters. That comes out approximately 40 joules. It's 40.5 joules. I just approximated. You can work out the details. Okay, so this force acting through 30 centimeters would give you 40 joules. Alternatively, 30 centimeters on the arc at the 10 centimeter distance is 3 radians. And I won't explain that. I explained it up here, just the definition of a radian. So that your delta theta in this case is 3 radians. So you still have the same torque that we had up here, but it's applied through a 3 radian displacement, angular displacement. So we're going to have to multiply that same torque, 13.5 meter newtons, the same torque, by 3 radians, and we're going to get approximately 40 joules. And again, the work done calculated by net force times distance in the direction of that force gives us the same thing as net torque multiplied by the angular displacement. 40 joules in both cases. Now, why do we get more work down here than we got up here? Well, 2 reasons. One way to understand it is to produce this torque at this distance, we need more force. And we're still moving through 30 centimeters of arc. 30 centimeters of arc is 30 centimeters of arc, whether it's here or here. So because we're closer to the axis, we're exerting more force and exerting through 30 centimeters of arc. Alternatively, we're closer to the axis, so that 30 centimeters of arc is 9 times as many radians because we're 9 times closer to the axis. Okay, so you want to sort those ideas out and understand in some depth how these two calculations are related.